Log on, tune in, find out. Another good idea from Cambridge.
Welcome again. It's my pleasure to introduce Gary Seitz from Oregon, who will tell us about unipotent and nilpotent elements in simple algebraic groups.
Right. So this is a big project that Martin Liebeck and I have been working on for a while. I guess ever since I was a graduate student, I've been thinking off and on about groups of Lie type and algebraic groups, and all, God, it's been forever. And all through that time, all those years, there's this, been very disappointed that something very basic to the theory, I really had no good understanding of, and that's unipotent elements and nilpotent elements. And you would think that if you were studying and proving theorems about these groups, you would at least have some idea about the conjugacy classes. And well, so at some point I vowed that I would try to figure this out to some degree, and of course it took me forever. Now I'm finally doing it and getting somewhere, I think. So so the goal is to understand for simple algebraic groups, and then because of that for finite groups of Lie type, all the nilpotent elements and unipotent elements, or nilpotent elements in the Lie algebra, the unipotent elements in the group, conjugacy classes, and precise centralizers. And I'll just say that. And so that's the goal. And if you know the literature, this is sort of all over the map. And for the unipotent elements, there's a great number of papers and small characteristics, often using different methods and different notations. And in some cases, it's not entirely satisfactory. And then for nilpotent elements, there's a lot missing. For example, you can't really find the reductive parts of centralizers, except for one or two examples. So anyway, that's our goal. And so we're closing in on the complete answer here. And I'll just make a few comments, and then I'll state the sort of the main parts of the analysis, and I'll tell you little bits and pieces about some of those parts maybe. So the main thing to report is that what we do is largely independent of everything that's been done before, which is either a good thing or a bad thing, depending on your point of view. In particular, we do not assume that there are finally many classes of either unipotents or nilpotents. We avoid machine calculations. We wanted to do something which a human could do, which means you have to have a good enough method that you can understand it and be able to do it, which is one of the goals. And what's particular to, I think, this analysis is that there's an enormous advantage of doing the nilpotents and unipotents together. And I'll try to indicate why that is. And so, okay. So let me just give you the basic plan. So it goes roughly like this. Plan. And these are in pretty good-sized chunks. So you do the classical groups first. Now remember, I'm allowing all characteristics, so P equals 2 is serious for classical groups, and I spoke about that yesterday at Cambridge. Yeah, 2. And so using this in some places, you now settle the 8 for nilpotent elements. As you find all the nilpotent element classes in the Lie algebra of the E8, and you find the precise centralizers. And what we really do is produce some elements, and we find the precise centralizers, and then we check completeness. and G is Q. I'll just write this down. That you can, once you find precise centralizers, you can use Lang theory to descend to the finite group on the finite Lie algebra, total up what you have. You could use a machine for this, for adding, or you could do it by hand, which I've tried. And if you get the right number, which is Q to the number of roots, you're home free. And by the way, this is for nilpotent elements. This is actually the only proof in the literature as well that you have the right number of classes. And 3, then after you've got that, you now settle. So I'm basically, having done this, I'm focusing on exception groups. Now settle other exception groups. And the way to do that is actually fairly easy. Just notice that E7 is a centralizer in EA, in particular A1 by root groups, E6 centralizer in EA2, etc. F4 the centralizer in G2, and the other way. So, if you know E8, you can sort of descend to these other groups. There's a couple issues, but basically that's the flavor of the argument. And the last part is Unipotent, which is true. And the point is that, as I hope to convince you, that this part comes out fairly nicely once you have nilpotents, except for a handful of situations that are characteristic. Okay. So I want to just try to give the ideas, some of the ideas in all this. So we start off with a simple algebraic group. Closed field of some characteristic P, and this is sort of what I said some of this yesterday, so I'll repeat it here. We'll take X to be either U or E. So U is unipotent. And G, E is nilpotent. The algebra. Okay. And we eventually want to find classes, and we want to find centralizers. I mean precise centralizers, component group and all, that you need in order to descend into the finite groups. So we know that this X is got some centralizer in the group, and in it it's got a maximal torus of the centralizer, and T0 equals 1 is an important case. Anyway, so that's an important case. And then the centralizer in G of the torus, which could be the whole group if T0 is 1, is a Levy L. And the Levy is the semi-simple part times the torus. Okay? And because we've now thrown away the torus, I can say that the centralizer in L prime of my X connected is unipotent. So far so good, and those of you that know the Ballard-Carter theory, this is sort of where we're going, although it doesn't apply in that characteristic. And so in this case, we say X is distinguished. Distinguished, I should say, in L prime. And I should say L prime works the algebra, but I'll stop saying that sort of thing. Okay, so let's, the first thing to talk about is distinguished classes. And I'll mention this. So we need this. Doing it in L prime is basically the same as doing it in simple factors of L prime. So we'll take X, a simple group, thinking of one of the simple factors of this Levy. And I'll just say how do I want to say it this way? So in good characteristic, I guess I should say L part already, that if you assume he is good, he is a characteristic, and X distinguished, and X, then the statement is this: then there exists a parabolic P sub X, which is Q sub X, L sub X, where that is the unipotent radical, and that's the Levy subgroup of this parabolic, such that special type of parabolic with the property that the dimension of the Levy is precisely the dimension of the commutator quotient of the unipotent radical, which barely gives enough room for a dense orbit on this quotient. That's what happens. What else do I want to say? And the orbit is dense in Q sub X, and now I better say, or the algebra of Q sub X. So, so that's one way to find the classes in good characteristic. You find the possible Levies, you find the possible distinguished guys by finding distinguished parabolic subgroups, and that way you get some classification. Now, I'll just say this, that the parabolics like this, they're also called distinguished, are fairly easy to find. For example, you always have the Borel subgroup like this, right? The quotient is simple roots, the top is the torus of the same rank. Bad news is that, but in a bad characteristic, this may fail. So what we do is this. We already have information for classical groups, but for all the exceptional groups, and for each parabolic like this in the exceptional groups, for example, in E8, there's a bunch of them, we produce explicitly an element. Now, remember, we're doing. I guess at this point I should probably. No, it's okay. So I'll just say this: for X exception, we produce a distinguished element for each such px, and it's exactly the same element for all characteristics. It's independent of the characteristic, and we find G of this x, which is the same as Cp of x. And we do this explicitly. This is this involves a bunch of calculation, but there's some absolutely beautiful things in this calculation which I won't be able to describe in this talk. It's the same for all characteristics, but the answer varies in the component group. And maybe I'll see some of that a little bit later for the unipotents in particular. Okay. Now, eventually, along the way, and I'll tell you how that happens, we find more. They find additional.
There is. You don't know that the centralizer is in G is the centralizer in P. You have to show that as part of what you're showing.
Of course, yeah. Additional distinguished elements. And we'll get to that a bit later. Okay. So now let's just start with So let's start back over here. So let's fix L equals L prime zero linear wavy, X distinguished, prime, the Algebraic prime, and I think we're still allowing Unipotent or nilpotent. And the first little proposition is this. So given this proposition, let P equal QL be a parabolic. Subject to G. Back to G. So they all may live in several parabolic subgroups as the Levy subgroup. That's one of those. And then you get a little result like this. And the dimension Cg of x equals dim Q of x dim L of x, and usually it's the same as this one with dim the Q opposite. So this is just the density of the product, but you get something on dimension. So let's just think about this for a second. From the embedding of X and L, you may already know something about the dimension of that centralizer. Q has a filtration by modules for L. So from that same embedding of X and L, maybe you know something about fixed points on those modules. Of course, this group is not going to be abelian, but usually anyway. But doesn't matter. You can do something with that. Anyway, you get some information about dimension, which is a start. Okay. And so now, I think I better start focusing on nilpotent elements. So now take nilpotents. And so now, and let's just keep, G may as well be E8 at this point, but anyway, we have, let's take our E distinguished, prime again. And we want to find, so maybe E is then one of these things coming from a distinguished parabolic subgroup. There. And then you find T, the one-dimensional torus. This is what Don was talking about, the character. The property that T is C, or the C squared B. So we have 2 on that element. Okay. And then let me give you another proposition, which is, so I'm trying to close in a little bit on this centralizer, and I've got something about dimension, and now here's something more. So let's take E and T as above, and further, T sits in L prime, in this place where it is distinguished. That has the effect of making it unique up to conjugacy in the centralizer in L prime of V. Okay. Then you get this marvelous little product. Unipotent radical centralizer times the centralizer G of T and V at the same time. Now, typically, but not quite always, this is a semi-direct product, and this is the reductive part of the centralizer. But in any case, this centralizer T and E carries with it the reductive part and the component group, of course. So if you want to understand the component group, the reductive part, this is where you look. If you're already sitting on the dimension of the centralizer, and you can find this thing, then you have a pretty good chance of knowing everything by subtracting dimensions to get the dimension of the important group. So this is a key part of the analysis. Going there a little bit. This is a very long story, so I'm just going to give you the overview, but I think you can maybe see roughly how it goes. Okay. Right. Next. So T determines parabolic. One of the confusing things for you guys is that even for us too, is that you're watching different parabolics go by. So the first one is where L lives, is L A. And now we're going to still some other one. So I'll just be careful, I'll call it P sub T. We usually call it P, and then we get in trouble. But anyway, and again, I'll write a Q sub T, L sub T, where L sub T is just a centralizer in G of T. And Q sub T sort of is just the product of root groups. You can bet T in some maximal torus, doesn't matter which one it is. The product of U alpha for which T has positive weight. Root element. Okay. Okay. Now, we also know from this, I'll just write that down again, the CG of E is RU, CG of E, times C of TE, which is RU, CG of E, times, well, this is C of T right here, so it's GL of E, L sub T, so I'm already doing that. And so I'm going to use the word generic to mean an element which sort of behaves the same in all characteristics, which is nearly all of them. There's a few quite different ones, and we'll see some in a minute. But I'll just say this much, that in the generic case, so if your characteristic was good, everything is generic. If it's bad, well, most things are generic, but there's a handful or so of ones that are not. In the generic case, here's what happens. CG of E is actually equal to CQ sub T of E and T of E. That is semi-direct. This is also reductive in the generic case, but never mind. I'll just tell you that this, again, this happens for almost all the situations. And one thing I'll also tell you is that CQ sub T of E is always connected. In any case. And that's because T acts on Q sub P without fixed points. The weights are all positive. If you think about that for a minute, you'll realize it can't possibly be since this centralizer is stabilized by T, there can't possibly be a component. Okay. Now there's some additional information which, for this generic case anyway, and in most cases, which is very nice and which is critical for unipotent cases later on. So let's just say an additional information. Goes like this. So again, assume E is in some sense generic. And just to make things, because this is not necessary, just to make things a little easier, and assume P has only even weights. If it doesn't, you have to make a slight change, but not very, it's a slightly different version of what I'm about to say. Okay. So the extra information is this. Then E, two things. E to the orbit is dense in L of Q C. Okay. Meaning that the dimension, the centralizer, is precisely the codimension of Q sub T, which is the dimension of L. And also, and this is particularly important for L, E plus that coset is actually equal to the orbit under Q sub T itself. So if you wanted to know what all the guys are in this orbit, it's pretty easy. You just it's the whole coset for any one of them, and then you can just find out what happens in the quotient. So you get precisely what the elements are in that orbit. Okay. All right, so this is all for the generic case, and I'll just say now that there are cases where this doesn't work. And let me just give you maybe an example one. Well, okay. So, let's just take an example. So that'd be easiest. So, this fails, for example, if you take your E and you find CG of E and the centralizer is too big. In other words, you have this E, which something which exists in all characteristics, and the characteristic 2 or 3 or 5 or whatever, you find that the centralizer is bigger than expected. So I'll just give you an example. So here's an example where this occurs. So we'll take E regular in D7. So what I'm talking about is that L prime is D7 labeled in E8. G is E8. That one doesn't go up. Okay. So here's what happens. That if P is not 2, then the centralizer of this guy is precisely U17A1. 19A1. We'll come back to this a little later for the unipotent element. And when P is equal to 2, things change. Namely, the centralizer being a little larger. So this sort of thing happens, okay? And it can happen in one of two ways. Either the unipotent part gets a little larger, or maybe the centralizer in up and L gets a little bit larger. But nonetheless, if you think about what this means, if you were pushing down to the finite group, that would mean that your centralizer is too big, the orbit's too small, and so you need another class to accommodate, or class or classes. Okay, so let me tell you what happens. It's exactly the same in all such situations. So, in such cases, you form something I'll call E bar, something related to E but different, which is E plus a single root element, carefully chosen. Carefully chosen. And then you show that you show that the centralizer G of E bar. This is sort of a tricky issue, but it's a centralizer G of E bar. Now I'll just say this quickly in passing, that the torus for E bar is not the torus for E. Nonetheless, this is the parabolic subgroup that contains the centralizer. It's a goofy situation, but that's what happened. And you do this, and all becomes nice. This thing is dense. I'll just write dense because it's not always dense in all of QT. There's another subgroup involved sometimes. Okay. And how do I say this? I'll just say it this way. E to the G plus E bar to the G gives the correct count. And I'll point that out right now.
Then still where? In the
Yeah, that's the point. So there's, also I can write down, and L, Q, so T is these two. By that I mean the product of our root groups where the root has weight of these two. The labels might involve ones in this case, I'm not going to worry about that. But anyway, that's where E lives. And maybe I'll just do that. Maybe I'll do it over here. So just to show you how this plays out and sort of the local nature of the information, let us suppose that we were taking fixed points under Frobenius here, that everything is connected, so that makes life a little easier. So you get one class in the finite group in each situation. So if you were looking at the orbit from here, you'd have the order of G of Q over something. What is that denominator? Over, what is it? Q to the 19, and the order of A1 sub Q would be Q squared minus 1. Okay. And, so I haven't told you what happens, well, I will in a minute. So now for this guy, which didn't look so good, we get the same thing with Q to the 21. Okay. And I can't go on unless I tell you what E bar looks like in the centralizer. So the centralizer down here, E bar is U22, I hope. And so you add to this over Q22, and I hope we do this right. I think you'll discover that you get exactly the other side. Okay. So what that means is that this E bar is precisely, it's precisely enough to fill out what you're missing. And this is a general situation. You don't have to, when you're missing a class, you don't have to look all over the world for a new class to take care of things. It comes out just like this, and the addition can be done just in one, this one class.
So do you say it's always only one new class which comes, or?
For the exceptional groups. Now, so well, one new class per E that goes bad. I mean, so it's only one E bar required. For the class groups, you might need a lot.
And how do you know, so how, you have this new E bar, which is visibly not conjugate to your E, but how do you know it's not conjugate to some other thing you've constructed somewhere else in the list? You look.
Because it's centralizer in a
So
different
you
place.
actually look at the, yeah.
Yeah. Good question. Okay, maybe I'll let's see, I've got enough time, I think. Let me just write down, because you don't see it too often, the exact new classes that you get in at least one case. And if you read Carter's book, for example, at the end of the section on this, it says that there are 6 new classes for E8 and characteristic 2. And I can write them down for you now. By the way, something like this E bar, you want to give these things names. So this is D7, and this occurred in characteristic 2, and so we just call it D7 sub 2 to indicate it's this information. Okay, so here are the new classes. And this is E8 equals to, remember we're doing nilpotent. It's different for Unipotent, and we'll see why in a minute. Okay. So here they are. There's this one we just did. There's this one closely related. There's sort of a next, whatever that means, regular class in D7. There's a D5, A2 lady, which something goes wrong. And these are the students. Okay. There's 3 more. There's an A6 sub 2, which lives in E7. And also E8, it becomes new. Now, there's different notations. Now, I'm using notation from the talk yesterday, so those didn't attend that would know that that's okay. I could give it a different name, but W34 plus W2. This is something new that only exists in characteristic 2, and is an extra distinguished class in D6, the class with the 12. So there's one more distinguished class than usual in characteristic 2, orthogonal 12. Ditto for orthogonal 14. 7 class, and these are all non-standard. So in some way, they're not anything too mysterious. It's just something which is fairly simple to describe. The centralizers work too big, so you're adjusting to get into the class, and that's where it is. So this occurs because some other class in D6 had a bigger centralizer than it should have, and this is needed to fill it out. So this would be something else up to in D6, but I'll look at that. Okay, fine. So let's pass the unipotent. So at this point, I'm assuming that I know everything about nilpotent classes. I have explicit representatives for the explicit expressions for representatives, precise centralizers. This takes a long time to produce, but we've got that. So now let's move on. Now I'll just say that it's not quite done. Looking very good, but not quite done for people. There's a lot of work already that's been done, and it's looking quite promising. Okay, so here's the very simple idea. We have these. And maybe some e-bars. And we'll ignore these for now because the extra ones, we'll ignore them for right now. And so we have these e's presented like this. And some are root elements, specific coefficients, and usually Ci is 1. I think it's always plus or minus 1, so it lives in the base field, which you would like to know. And you do the most obvious thing possible. So let's set U equal the product of U alpha I Ci. And then you say, wait a minute, the order matters for group elements, it doesn't for nilpotent elements. And any order, it doesn't matter. Now, the big problem here is this. The nilpotent element came equipped with a T. And you got some sort of factorization from the centralizer that gave you a hope of putting it in a certain place. Okay? For you, there is no such T. And so what's the centralizer going to be? Well, you certainly don't want to search all double costates and work it out. I mean, if you've tried that sort of thing, it's not a lot of fun. So you want to have some way of doing it. So here's another proposition, which is, still can't believe it. This was, well, I'm going to say this. This was proved on day 1 of the life of my one of my grandkids named Max, and so I now call it Max's Lemons. He got an early start in mathematics. So if I was sort of irrelevant sitting around the couch, not knowing what to do on that day, so I did some mathematics and got this lemon. So if E and U as above, and E, this is still written in EA code, and E generic, means everything is just like it should be in characteristic 0 or whatever, then CG of U is CG at C P sub T, right down in that same parabolic you had for E, which gives you a much better chance of finding the centralizer. So this is a very important piece of information. Okay. Gets a little bit better. Again, let's make things a little easier and assume P weights on L of G are even. It's only slightly different if they're not. And then, if you recall what I said, EP of T is dense, and L of QT. Now, Q over Q prime is isomorphic, at least in the reaction of this, whoops, L sub T, I guess, product of root groups to L of Q over L of Q prime, which is isomorphic to L of Q sub 2. This Q over Q prime is generated by things of weight 2, and so you just get this. And under this isomorphism, because of the stupid way we wrote down U, you find that UQ prime corresponds to E under the isomorphism. So what are the things that get you? So the centralizer, I'll just write it this way, of UQ prime. Does that make sense? Q centralizes Q over Q prime, so I can write that down. This looks like, well, that's L. Oh gosh, see, I always do this. I need a T on everything, and of course I got T on half of them, but not the others. I'm sorry. Q, this is the only parabolic that matters at this stage. This is the same thing because of this isomorphism, but just C L sub T of E. We know that group. Unfortunately, we don't know. I mean, that just centralizes the coset and not U itself. That's too bad, but we're going to get past that in a minute. Okay. So, in the generic case, which we're assuming, you have things like this. L of CQ of E, Q sub T, is the centralizer L of Q sub T of E. So I'm just giving you the best of all possible worlds. And then you can make the following argument that, I'll just write down the answer first. The dimension of C Q sub T of U is less than the dimension, this is generally true, of C L Q sub T of E. This is just a consequence of writing down the element the way it was, which is now, by this assumption or generic situation, dimension of CQ sub T of E. Okay, so we now have that the dimension of CP, P sub T of U, is bounded, well, on top it's at most that, and below it's less than or equal to that. And so you get, so we're now in fine shape. So this argument goes very smoothly in the generic case. basically no work at all. Probably should have erased that. And so in this case, we get dim C p sub t of u less than dim C p sub t of e. But E was in the dense orbit, so it has the smallest possible centralizer. So therefore, but also, because of that, dim C p sub t of u is always greater than or equal to, I'll just say P over Q, which is the same exact condition. And now we get sort of equality of everything. So MC Q sub t of u equals dim C Q sub t of E. Because of that, you get the orbit of u nice, that the u q sub t is precisely u q sub t prime, all elements in that coset are fused. Okay. And because of that, you can use a Frattini argument, if that makes sense to algebraic group people. You then get from this that the centralizer in P sub t of u over centralizer in Q sub t of u is actually isomorphic to C L sub t of e. Before, before it mapped into it, but before we knew that this thing mapped into C L sub t of E, now it's onto, and so we're done in this case. So at this point, we know the following. So therefore, we have that. C p sub t of u over. I'm just repeating myself. It's isomorphic to C p sub t of E, C q sub t of E, and the dimension of unipotent parts. The centralizers look exactly the same in that case. Okay. So you sort of think that all is good, and this is true in the generic case we've been talking about. So let me tell you what can go wrong. No, not everything is good. So for most of this goes through with variations for bad primes as well, but not everything. And here's the type of thing that can go wrong if you're and does for any bad prime. So first of all, so I'll just say, what about non-generic? We saw for E that you got some changes. And so bad primes are what come in here, but even for bad primes, you get some nice things happening. But here's what's different. It's not necessarily true that CQ sub T of E, I'm sorry, U, equals CQ sub T of U. Connected. It was for E because the action of T forced, we don't have a T and it doesn't force it therefore, because it's not true. Okay, and what we show is, at least for the exceptional groups, although I've got some concern about F4 equals 2, the centralizer in Q sub T of U is this. That it may not be connected, but it's only off by the fact that U sticks out of its own centralizer. That's part of it. So, for example, if U is regular element displays the whole issue in this case, that the centralizer E8 of U equals U8, U8 by U. So if P is bigger than 5, that's good, you get U8. If P is equal to 3 or 5, the bad times, then you get U8 ZP. U sticks out and gives you word P only. And if P is equal to 2, you get U8 Z4. Some people think of 4 as a prime. If you do that, it's still ZP. So the other thing I'll say, and then I'll stop. The other thing that happens is that the new classes, the things that were E bars before, are somewhat different. And I can illustrate very well where that sort of happens. And so let's just take an example, and we'll take our old friend E equals G7. And what we saw before was that for P different from 2, CG of E was U19A1. P equals 2, CG of E was U21A1. And then we had an E bar, and centralizer of E bar was U20, what was it, 22?
Yeah.
Yeah, so the dimension has to be the same as that to get against. Yeah, and, okay, so what happens for the unipotent element? Here's what happens. For P, so P different from 2, unipotent, here it is. CG of U is U19A1. Right? Well, yeah, it's the same as that one. And for P equals 2, CG of U doesn't change much. It's U19A1 C2. So you still have the density you had before. You don't necessarily need well, you don't need a new class to cover what you're missing, but you do need an extra Z2. Why in the world would you need an extra Z2 when it wasn't there for any other characteristic? Well, you need it because of this. That D7 itself has its regular unipotent element having its centralizer sticking out of the connected component. So that's what happens, and because of things like that, you're going to find out that there are fewer of these extra classes for the unipotents than for the nilpotents. When there is an extra class required, in other words, you go through this and you find out something like this happens for U as well as for E, then you need an extra class, and it's U bar, exactly the thing you would write down for the E bar in nilpotents. So there's this really lovely these connections. I mean, I guess the point I'm trying to drive home is that the nilpotents are the way to go because you get information on unipotents right away, and unipotents are much harder to work with in general. I guess that's it.
Questions?
So what is this carefully chosen E alpha?
Right. It's something of weight larger than 2 for 2, and you have to make sure it doesn't live in a certain commutator space. So if it has weight 3, you want to make sure it doesn't live in the commutator of weight 2 stuff we leave. So as long as you stay away from that, it's usually fine.
Any other questions or comments?
Okay, I have a question. Max's lemma,
Yeah.
is it, why don't you give us an idea of the proof? You said the other day, you said it was easy. It's not that easy?
It's not that easy. I mean, you basically have to look at a double coset of something that you've got a W that might be in a double coset that centralizes your unipotent element, and very carefully work out what that says. And if you do, you find that you have some intersection of parabolics. The centralizer is sort of there, and the element's here, and you find that E is sort of carried along. And so you just keep E in the picture, and you eventually show that you have to be in the parabolic piece of P. Okay, I'll show you later.
Let's thank the speaker again.